Hello guys, good day everyone. Welcome to this class on regression. And before I proceed with the presentation, allow me to start with the prayer. Dear Heavenly Father, I just want to praise and thank you for this new day. Um, Thank you for your goodness and your grace that we have the strength to get up to a new day. And I pray today, please give me the wisdom that I may be able to impart this lesson clearly. And I pray also for the viewers of this video that they may have the understanding, the knowledge, and um, to learn the lesson from this video. Lord, I give to you all the glory and all the praises. May your name be exalted and be glorified in everything. I acknowledge, dear God, that without you, I can do nothing. Help me, help my students. In Jesus' mighty name we pray. Amen. Okay, so good day, everyone. Welcome to this class in regression. I hope that everything is well with you. And today, I will be discussing regression. Allow me to have some review of what correlation is and how it is compared to regression. What's the difference? What are the points of difference between correlation and regression? Well, basically, correlation and regression are both measures of or tests of association or relationship. Okay, so that is why in my previous video on correlation, I used the regression function of Excel to test for correlation between the two variables, because regression is based on correlation also. Okay. However, correlation is a lower step, or should I say, regression is a higher step, is a step higher than correlation, because correlation only tells us what is the type of relationship and what is the degree of relationship between variables. However, regression tells us whether one variable affects another, or whether one variable affects another, or what changes it affects on another variable. So we have the predictor variable and we have the outcome variable. So with regression, we try to predict, or we try to know whether one variable, which is the predictor variable, affects another variable, which is the outcome variable, your x and your y. So here in this table here, we can see that correlation is not used for prediction. However, regression is used for prediction. Okay, so in correlation, the test of association includes only two variables, meaning bivariate association. So we correlate the x with the y. However, in regression, we can have bivariate association or multiple associations of variables. So we can predict several or more than one predictors on a single or on one outcome variable. So we can use, we use here multiple regression. In correlation, the x and the y variables can be interchanged. because you only want to know whether the two variables go together in the same direction or in opposite direction. However, in regression analysis, your input and output variables should be fixed. You don't interchange them. Okay, so whatever that you assign as the x, it should remain as the x, and whatever you assign as the y, it should remain as the y. Okay, so in here, in the graphical presentation of correlation versus regression, we can see that here in the correlation, the data points are plotted here. For example, we have correlation point here, 1 point here. We can see that this point, okay, this is a data point which scores on the x variable and score on the y variable. Say, for example, there is a correlation between study hours. This is our x, and grade. Okay, so we have here, let's say our study hours would vary from 1 to 5. 1, 2, 3, 4, 5. So 5 would be highest a number of study hours, 1. And then our grade would vary from 1, 2, 3, 4. So 1, 2, 3, 4. So we see here that this data point, let's say, this may be a person who devotes, let's say, 4.5 study hours per day, and his grade is 4.0. And let's look at this data point here. This is someone, say for example, this is Jim, whose score on study hour is 1 hour. He devotes 1 hour of study in a day, okay? And his grade is 1.0. Okay, somebody here, say sabihin natin this is Roy. He devotes, sabihin natin, 4.3 hours per day in studying, and his grade is 4.0. So this one, these are data points, and in this graph, it shows that there is a positive correlation between study hours and grade, meaning to say, as you increase study hours, you also increase the grade. As you increase on the x, you increase on the y. Now, when we say negative correlation, there is an inverse relationship. So we would expect that in an inverse or negative relationship, the dots, the data points would look like this. It would be going downward, meaning to say, as you decrease on x variable, as you lessen your study hours, you increase your grades. That would be a funny situation there. So, and if you increase your study hours, your grades would decrease. So that is an inverse relationship. That is a negative relationship. Okay, so I am plotting here. I have just described to you, what is a positive relationship and a negative relationship. Negative relationship, that does not mean that there is an absence of relationship. It only means that the direction of relationship between the two variables is inverse. Opposite sila. So that is the type of relationship. Relationship also, correlations, can also be determined, okay, The strength of relationship or degree of relationship can also be determined by correlation coefficient values. If you remember from the previous lecture, we have the R, which is the Pearson R value, that is the correlation coefficient, and it varies from an absolute value of 1 to 0. Okay, so we have, so it is on a continuum, say for example, negative 1.0 and positive 1.0. So any value outside of 1, greater than 1, that would alarm you that you have done a wrong computation, because correlation coefficient varies only from 0 to 1, the absolute value of 0 to 1. The nearer you move to the 0 point, it indicates a weaker correlation or a weaker relationship, and the nearer you move to the value of 1, it indicates a stronger relationship between the two variables. So that is correlation. Now in regression, however, we try to see, okay, so these are now the data plots. You would see here, these are the data points. These are the observed data. Now in regression, we try to predict what is the model that would best explain the relationship of this X and the Y. We try to find the best fitting line that goes through these data points, okay, and minimize the residual or the difference between our prediction and the actual observed data points. So this is our prediction, this line here, and we want to test through regression analysis. We try to test whether this prediction, this line that tries to predict the relationship between the X and your Y is the best model that would fit all of these observed data here. Okay, so as much as possible, we want that our predicted line would fit all these observed data points. Kailangan, gusto natin there would be less difference or less residual between the line that we have fitted here and the observed data points. Okay, so now in regression, there are some assumptions, the same way also that in correlation, there are some assumptions that we have to meet before we accept the output or the result of our regression analysis. So we say that in regression, we have to check whether the residuals are independent, okay? Meaning to say that there is no autocorrelation in these residuals, okay? So that is what we mean by residuals are independent. Now, if we are doing a cross-sectional study, meaning to say the data is not longitudinal, the data set was not gathered over time, it is not a time series study, then we should not worry about, you know, residuals being independent, meeting this assumption of residuals being independent, because we assume that in a cross-sectional study, we assume that the residuals are independent, so we should have no problem with it. Now, we should worry if this if your study, if your data set was if your data set was gathered along a time series data, okay, along longitudinal way. Now, for you to test whether you have independent residuals, the residuals in your regression analysis is independent, so you can meet that assumption. There is a test in regression analysis that is called Durbin-Watson test. This one, the Durbin-Watson test. So if you have a statistical value between 1.5 to 2.5, then that would indicate that you have met that assumption of independence of residual. Okay, another assumption that we have to meet before accepting the results of a regression analysis is what we call homoscedasticity. This means to say, okay, this one here, homoscedasticity. This means that the residual should have a constant variance. Okay, so ito yung ano niyan. Ito yung itsura niyan. The residuals, meaning to say, this is the line here in this picture. The line here, this means this is the line. This is our fitted line. And then the residuals, these data points are the residuals. The difference between our prediction, the residuals between our prediction, the difference between our prediction and the observed data. Okay, so makita natin that the data points are scattered along this line. There is no observed pattern that we can see from this. So this graph represents a good picture of residuals that have a constant variance, that are approximately normally distributed, and residuals that are independent of one another. So dapat ito, yung mga data points na to, ito yung mga residual points, they should be scattered all over the graph. They should not be creating some form of pattern. So the most useful graph for analyzing residuals is a residual by predicted plot. This is a graph of each residual value plotted against the corresponding predicted value. If the assumptions are met, the residuals will be randomly scattered around the center line of 0 with no obvious pattern. The residuals will look like an structured cloud of points centered at 0. So, ito siya. This one here. So, this is, we can see that these residuals, these data points over residuals are scattered all over the graph. So, that should be a good picture. Now, another picture that would be alarming to us is this kind of picture wherein the residuals form a curve. There is a curve that we can see in here. So this indicates that the residuals, we need to say the difference between our prediction and the observed data form not a linear relationship, because we are assuming in a regression analysis that there is a linear relationship between our variables. When you say linear, it's like this. Ito, ang line natin, ang data points natin forms a straight line. Walang curve doon. But in this here, we can see that there is curvature of residuals there. So that indicates that there is over prediction, meaning to say the linear model systematically over predicts some values. So that would result in negative values and under predicts others. So that would indicate the positive values. Okay. So over predicts and under predicts. So that would be a bad prediction. That would be a bad model natin. Okay? So if curvature is present in the residuals, then it is likely that there is curvature in the relationship between the response and the predictor that is not explained by our model. A linear model does not adequately describe the relationship between the predictor and the response. Okay, so now another is when we look at the graph, we see heteroscedasticity, meaning to say the residuals for, a fan, just like this one. From here, maliit yung distance from this, and then pataas, ano siya, it is fanning out, parang it forms a cone. It shapes into a cone. So yan, that indicates heteroscedasticity, meaning to say the variances of our residuals are not the same all throughout. So as y increases, the errors also increase. So if the residuals fan out as the predicted values increase, then we have what is known as heteroscedasticity. This means that the variability in the response is changing as the predicted value increases. This is a problem in part because the observations with larger errors will have more pull or influence on the fitted model. So ibig sabihin, these residuals here that are far from this line here, from the zero line here, they have larger errors and they may tend to be influential on our whole model. Okay, so siya. And what we want is residuals that is approximately normally distributed. So if you will look at here, this is our prediction, line of prediction. Okay, the data points are just near along this line. The blue points here, they just lie along this line. They are not too far away from the predicted line here. So that is what we call an approximately normal distribution. Now these are visual inspections of graphs. Now there are tests that we can do in order to check whether we have violated this these assumptions. For heteroscedasticity or homoscedasticity, pag sinabi homoscedasticity, meaning to say the residuals of constant variance, and if we have violated that, then we call that heteroscedasticity. We can do this test for more precision. We can do statistical test of this by doing the Bruce-Pagan test. Okay. So with the Bruce-Pagan test, we check residual versus the predicted value. So it is also a hypothesis testing that says in its null hypothesis, it says that all the variances are equal. So meaning to say homoscedasticity. Now, as a researcher, our goal is to achieve this homoscedasticity. We want the null hypothesis to be accepted, not the alternative hypothesis in the Bruce-Pagan test that says all error variances are not equal. Now, for the normality of the residuals, one way is to plot a histogram of the residuals. Okay, we make a histogram of the residuals and then try to see whether the residuals are far from the normal distribution. Or we can use the Shapiro-Wilk, the Kolmogorov-Smirnov, or the Agostino-Pearson. However, the problem with this is these tests, however, are sensitive to large samples. So they conclude this test, Shapiro-Wilk, the Agostino-Pearson, they conclude that the residuals are not normal when the sample size is large. So it is better still to look at the histogram of residuals. We try to set out a histogram of residuals. Now, for multicollinearity, another addition of assumption is the multicollinearity if we are doing multiple regression. Okay. In multicollinearity, we want to make sure that the independent variables or the predictors are not correlated with each other. Otherwise, there would be some overlapping of functions there, multicollinearity. Now, here, I got here some data. Actually, this is, I tried to rename based on the data from the burnout from the ProQL. I just renamed the labels. So say for example, you want to know, this is a multiple regression. You want to know whether age and task procrastination significantly predict test performance. So you have two independent variables, or you have two predictors. You have age as your predictor 1 and task procrastination as predictor 2. Okay, and your outcome variable is test performance. Okay, so you've got there test performance, your outcome variable. So your age is your predictor, and task procrastination is also your predictor. So you set up your hypothesis. You say that age and task procrastination do not significantly predict ProQL, and you say that age and task, for your alternative hypothesis, you say age and task procrastination significantly predict ProQL. Now, so regression, we try to come up with this. We say that there are two predictors for test performance. That would be age and task procrastination. So we now try to predict, okay, using this model. Okay, you just don't make some predictions from, randomly. You try to pull out, factors from somewhere else. So you try to make some model. So you write your model as this: y. So any dependent variable, any score on test performance, which is represented by y, is influenced by BO, or what we call A, or the intercept. This is the intercept. When you say intercept, this means to say the value of test performance, your test performance score, without yet plugging in the factors of age and task procrastination, without yet plugging in any predictor there. So what is the value of intercept plus, you have here your first predictor. So you have here the slope of the first predictor, which is age. Okay, sabihin natin B1. And you multiply it with the raw score of age times age plus the slope, or beta, the slope for task procrastination. So let's have these two. This is task procrastination times the raw score for procrastination plus some error term. Okay, so this is now our model for prediction of test performance. This is test performance. Okay, so we say that test performance is influenced by intercept plus age plus task procrastination. Okay. Okay, so dito pa ang concept nito is that based on your observation of data, you see that let's say here you have age, and then you have task procrastination here, and then you have test performance. And you say that, okay, now if the age is 15 years old, the task procrastination is, let's say, 38. The test performance is 60. Now, if the age is 20, task procrastination is 25, and the test performance is 80. Now, if the age is this is the observed data. The age is, let's say, 35. The task procrastination is 18, and the test performance is 90. Now, if you say, what would be the test performance if the age is 28 and the task procrastination is 24, then what would be the corresponding test performance? Now, how about if the age is 12, the task procrastination is 40, what would be the corresponding, what do you think could be the predicted test performance? So we are now doing some predictive analytics. Based on this observed data, we are trying to predict the corresponding outcome score based on this given scores on the X's. So using this model, regression model, okay, we use this. Now, we are performing multiple regression in order for us to see what is the value of this. What is the value of this? Because this would be given, the X1, the raw scores for X1 and X2 would be given. And we want to also know what is the value of this. So we can know how to compute for this Y predicted Y score. So, ito siya. Okay, so that is prediction. So we have here a given, look here, the age is an interval ratio data. This is continuous, procrastination is continuous. Later on, I will tell you, I will teach you how to know how to do this if you have a categorical variable. Say, for example, gender. Okay, so say, for example, gender. So you have here male. Let's say this is male. This one is female. So what would you do if it as part of your prediction that gender affects test performance also. So, but this time, allow me to show you how to do this with age and procrastination performance. Or maybe I will show you na lang ngayon. Let me copy this. Say course major. Course major. Mhm. Okay, so we have here a course measure. Course measure is a variable that is categorical. Now, say for example, we have course measure here in our in our in our prediction. So we have to do this. Y, predicted Y is equal to the intercept plus b b1 x1 plus um, b2 plus, okay, our course measure, I there are A, B, C, D. There are 4 course categories of course measure. So we need to make for categorical variable, categorical predictor variable, we need to make dummy variables for each of the categories in this predictor variable course measure. So we take each category as a separate predictor. Okay, so we say that ito pala, x2 plus b, we have this dummy variable 1. We have a times xa plus the slope for dummy variable b times b, and we have dummy variable for c plus error. Okay, for us to have another, kasi this is our B1, age is our B1. Task procrastination is our B2. And course measure is our third predictor variable. However, gagawin natin dito, so I could have space kasi the arrangement of your variables in Excel is, is very important. It matters because there shouldn't be, all the variables should be adjacent to each other in in the order of your model. So I have here, this would be A, B, C, D. I will put the Y here. There. So procrastination is our B2, so our dummy variable is, bear with me. So I will this here. Okay, so you would see that the course measure is mixed together. So you have C, you have A, you have B, you have D. So we have to filter, and we have to code, okay? Since let's say course measure A is one variable, one predictor variable, then we have course measure B as another predictor variable. So we need to have this A, and we need to put another column for B measure. So A measure, and then we have B measure, and then we have C measure. So your dummies, the number of dummies that you will create would be one less than the number of actual categories of your categorical variables. So if there are 4 course measures, then I would create 3 dummy variables. Okay, so what I would do here is that I will code. So let's say I will code A. For here, for A major dummy variable, I would code this A as 1, and all the rest that are not A, I would code as 0. So the same thing also for B major, I will code the B majors as 1 and all the other majors as 0. And then pagdating sa D, all would be 0, 0, 0. Okay, so let me do this. Actually there is so insert. I am looking for the filter. Ayun, filter. So I click data and then click filter. So you would see here, there are arrows here. So I will click this here and I will sort. I will try to look for all the A's only. So I will search for all the A's. So Excel will show me all the A's and I will code all the A's. Okay, so here you have You have the A's here, so I can code this A's as 1 and copy. All the way down, all the A's. And all the other measures I would code as 0. So I will copy. Okay. And so we have here 0. There you go. So Excel showed me all the A's, all the participants whose course major are A's. So I have encoded under the A major here variable as 1 and all the rest are 0. Okay, then I will filter again. Go back ulit ako. So I am back to my original data set. So you see Excel has inputted 1 for all the A major. So ngayon, I will be looking for all the B major so I can put them as 1 and the rest of the other course majors would be 0. So I will use filter and course major. I will deselect A, deselect C, and deselect D. So I only have B. Oh, there you go. So all the course majors B are shown. There you go. So I will code all the B majors as 1 and copy. And then I will have all the other majors as 0. There. And I will also look for, balik ulit ako, so I can go back to my original data set. And I will filter again. Yan. And I will click, drop this down, and I will look for C. So I will deselect B and A and D. And okay. So all C's, I will put 1. So lahat ng C nandito. Tapos yan siya. So there are 18 C's. There are 18 respondents who are majoring in C. And all the rest would be 0. Okay. Okay. So So, balik ulit sa dataset. So, malapit na tayo ma-fill in. And I will also have all the D's. All the D's. Okay, so lumabas si D. So we have, I will put all 0. Okay, so you have all this, all 0, 0, 0. And the next would be, so I have A major here, D major, C major. So our reference value would be D. So this means to say we are comparing, let's say for this one, we are comparing C major with D. So I will with this, I will put this here. Okay, and I will delete this column. Yun. I have to delete it so there would be no vacant columns here. So this is our Y. So this is our B1, this is our B2, this is BA, variable A, and this is our dummy variable E, and this is our dummy variable C. Okay. Bakit ba B ang nilagay ko? So this should be dummy variable. So this is dummy variable. This is dummy variable. Okay, so I will choose Control M. I will click Control M again. Oh, nawala si Control M. So for me to do this using the real stat, I have to click Options, More, then Options, Add-ins, and then I click Go. I will uncheck X real stat, and then OK. I will uncheck and check real stat for it to operate in my Excel. So Add-ins, and then click Go, and then click X real stat again. Okay. Okay, so we have here, I will click, press Control M. In the regression, I will choose multiple linear regression. I will click regression tools, and then I will click multiple regression, and then click OK. Now I will highlight all the inputs, all the predictors here. So That would be included in the input range for X. And then for the Y, I will plug in test performance. So I check column headings included with data, include constant term. Then the options here, so it will spew out regression analysis. It will also spew out residuals and Cook's D. It will also spew out Durbin-Watson test. This Durbin-Watson test is a test for independence of residuals and the normality test. Okay. And for the output range, I will choose this cell and I'll press OK. So this is now the residual plot. And we see that from the residual plot, seems that this one, the residuals are fanning out. There is a cone shape here. Anyway, let us try to look. So what are the things that we have to look into here? First, we look here sa overall fit of our model. So what is the multiple R? Ibig sabihin, this is the correlation. So the correlation of all of our predictors, combined together, okay, the association or the correlation of all our predictors combined together, okay, to our outcome variable, which is test performance, it is 0.65483. So that is 0.65483. That is well above the moderate association, and it is positive, meaning to say the higher the value of our predictors, the higher the value of our test performance. But for each of the predictors, saka natin titingnan. Now, what is significant here? We look here is this model significant? Can it significantly explain test performance? We look at the p-value here. Now, since this is in an exponential term, minus 20, so this means this should be good. We try to format this first into a number so that we will not be reading this as an exponent. Okay, 0.0. So this, we can say that age, task procrastination, and what's this? Yung course major can significantly predict that test performance. Now we will look into the for each of the predictors. Okay, so since the p-value is significant, now the r square. If you square 0.65, now 0.65 times 0.65, then that it should give you 0.42 or 0.43. So this is the coefficient of determination. Okay, so this is the coefficient of determination, the r squared. It is a statistical measure that represents the proportion of the variance for a dependent variable, your test performance, that's explained by the independent variables in a regression model. So it is expressed in percent. So that is 0.42. That means 42%. So 42% of the variance in test performance is explained by our model. Yan. And is it significant? Yes, it is significant. Now, let's look at the individual predictors. How are they? So this is our intercept. So let us try to change all these p-values into numbers. So we don't have to be okay, so we see here that this is the intercept. So the intercept is what is the test performance without yet putting in the predictors. It is 56.6839. Is it significant? Yes, it is significant. Now we look at age. Is it a significant predictor? Now we look at the p-value here. The p-value is 0.08. So again, our decision rule is p-value should be p-value the p-value should be less than or equal to 0.05, which is our alpha level. Which is our alpha level for us to reject the null hypothesis. Okay? For regression model ito. Decision rule for regression model. Okay? So the overall, all of the predictors together, that's age, burnouts, the major, overall, they are significant in predicting that test performance, that is 0.0. So that is significant. However, if we would look into the performance of each predictor, we can just say that the one that is significant is only task procrastination, because the p-value is 0.0. And this coefficient here, this is now the B. If we will go back to our model, task procrastination, ito coefficient, this is now the coefficient, the B2 times X2. So the B2, this means to say here that for every 1 unit increase in task procrastination, for every 1 unit increase in task procrastination, there is 1.27 unit increase in test performance. So 1 unit increase in task procrastination, this is quite interesting. Well, anyway, this data is, ano lang to, ginawa ko. Inano ko lang, this is the data from the ProQL and I just renamed it. I just renamed it. So test performance, task procrastination. This one, this is, this p-value is significant. Now, ito naman, A major, how do we explain this? Our reference value is the D major, the students who are majoring in D course. So we say that students, those students who are majoring in a course have test performance which are less 3.35. Yung test performance nila ay less than, decreases by 3.35 in score than those who are majoring in D. Okay, so we are comparing A major with the D major. Okay, now ito naman, we say that those majoring in B major have less, okay, their scores is 1.3 or 1.29 less, okay, units, 1.29 units less than those who are majoring in D. And dito naman sa C, those students who are majoring in the course, in course C, they have, their score is what's 0.85 less than those who are majoring in D. So, but is it significant? No, they are not significant because the p-values are greater than 0.05. Okay, so these are not, so it seems lumalabas that task procrastination is the only predictor variable that is significant in predicting what's this, test performance. Okay, but it could be that this model is significant because of the presence of the other predictors. We can test that by performing another regression wherein we try to eliminate all these not significant predictor variables. And if the adjusted R square is the same, then we can say that it was only the task procrastination that really did significantly predict test performance. Okay. Ngayon, in testing for assumptions, since this is a multiple regression, we have to look at the VIF scores. Okay, we look at VIF scores only for the variables that are continuous, not categorical. So, ito lang ang titingnan natin. So, itong VIF scores would tell us whether there is correlation, high correlation between age and task procrastination. So that would be a problem if the correlation between age and task procrastination is high. So that would indicate an overlapping of function between age and task procrastination. And since the VIF is less than 10, then we should be good about this. So the value of VIF should not be greater than 10. So we can proceed so that we will not violate multicollinearity assumption of multiple regression. Now, if we will look at Durbin-Watson, the Durbin-Watson statistic tells us that it is 2.04. So meaning to say, ito, ang null hypothesis kasi ng Durbin-Watson says that the residuals are independent, and the alternative hypothesis says that the residuals are not independent, or say the residuals are dependent on each other. So meaning to say there could be a problem in autocorrelation. But since it says here no, so we can be happy about this result of Durbin-Watson test. And since this is a cross-sectional data, the assumption on independence of residual would not be a problem for us. It should be a problem if we have a longitudinal data set. Now, the Shapiro-Wilk test would tell us that the normal, well, the residuals, the distribution of the residuals are not normal. Yan. Ito yung sinasabi. Kaso, ang nakikita natin is ito Shapiro-Wilk, this could have a problem, and D'Agostino Pearson, this could problem for us kasi si Shapiro-Wilk, they are sensitive to large sample data set. So let us try to see residual against the predicted Y. Ano yung sabi dito sa ano natin? Draw histogram of residual. We should draw normality of residual, or we can draw a plot of predicted Y and the residual. So let us try to see. Scatter. So our residual here, it shows heteroscedasticity. We have a problem with our residuals. So that it is the graphical presentation shows that it only confirms the Shapiro-Wilk test that there is that the residuals are not normally distributed. Well, anyway, so if this is the case, the statistician would have to do some troubleshooting of the data set. Ang gagawin niya dyan is try to delete the cases that whose residuals are very, very large, and then try to see if there would be an improvement on the model. So may mga case deletion siyang gagawin dyan in order to, because outliers could be a problem in this case. Kaya nito, this one, these are outliers that could pull the data very badly. So these things may have to be looked into. Kaya dito, we look at the residuals here. Like, ito, mga residuals na malalaki. Yun, standardized residuals na malalaki. So, titingnan yan. And if this would be taken out, omitted, what would happen to the regression model? Would it improve or not? Yun siya. Okay, so that's it for our regression. Okay, ito pala. How do we know how many samples? So, for us to determine how many samples should we get for regression, we look at linear multiple regression, fixed model R2 deviation from 0. Now say suppose we have ilan ang variables natin. We have age and task procrastination. We have 2 predictors. And we try to check for effect size of, let's say, medium, at least 0.15, and alpha level of 0.05. And let us have a modest 0.80 power. So let us compute for the actual number of sample. So we should need at least a total sample size of 68, it says, for a predictor of 2. Now, for dun sa predictors natin, we have how many? We have 3 dummy variables plus 2, so we have 5. Let's calculate. So we should have at least 92. However, don't rely on this 92, that if you have reached 92, then you stop gathering data anymore. You consider also that there could be mortality of your data, meaning to say there could be some cases that needs to be deleted in case if the residual plot is ugly. There are some cases that you have outliers, influential outliers that you have to delete from your data set. So you have to run the regression again without the influential outliers. So there would be cases that would be omitted. Okay, so you look at the standardized residual. The rule of thumb here is you look at the standardized residual. If there are residuals that are higher than 1, you try to consider it. And then try to do again another regression. You perform another regression and try to see if the model improves. How can you say that the model improves if the R square, the multiple R, is improving, meaning to say tumataas ang value nito? Then that means that the cases that you have deleted were really influential on your model. They tend to pull down yung model ninyo, yung value ng model ninyo. So that's it. In this video, I have talked about when to use regression, how is it different from correlation, what is the function of regression, multiple linear regression, and how to plot the statement of the problem for a multiple linear regression, and how to check for the violations of assumptions of multiple regression using visual inspection of graphs, and some tests that are in the real stat, and how to interpret the results of the regression analysis here, and the material that I have posted on reporting on regression result in our school book. You check it out, you read it, because it it explains on how to report the regression results using APA format. So that should be your guide on how to report it. Okay, so good day, everyone. Have a nice day ahead.